Hi everyone.
I need to.
Sorry,
I
Barak, you
cannot.
said something?
I cannot press. I don't see the mouse. There's a problem.
Okay, let's wait.
I don't know what to do. How do I do this?
You can't move to the next slide?
Whoa. Yes. I think now
Uh,
I can. No, I cannot. I can. Okay, good.
Now we can. Okay, great. So today it's a pleasure to have Barak Zackay from the Weizmann Institute, and he will tell us about the current state of ground-based gravitational wave astronomy and the efforts to study the origin of compact objects in relativistic binaries. Please, Barak.
Hello. Thank you for inviting me for this, and thank you, Shachar, for organizing this gravity seminar. I think it's a good idea that the Israeli community will have some seminar in this subject, and my students enjoy it. So, thank you, Shachar. A little bit about me. So I'm not the standard GR person. I don't know if there is a standard GR person, but I'm not that. So my main tools are algorithms and statistical methods. The goal, so I'm a physicist at Weizmann. So the goal is to make discoveries in astronomy. And in every project, every modern project in astronomy, data analysis plays a key role, especially in gravitational waves, because of the 1/d scaling. Basically, whatever improvement you make, it automatically translates to a much larger volume of discovery. So this is especially for gravitational wave astronomy, let's put it this way. And many times this thing is very beneficial because improvements I've done in the past translated to other fields, other surveys, and it was very beneficial for me. And many times the data is underutilized. This is not a criticism of any field. This is going to happen and last forever. Okay, so there's always places where we can improve. There's always things that we could have searched and did not search. And there are always improvements in algorithms and data analysis tools. Okay, so my group is quite large at this point. And we are focusing on gravitational wave astronomy, on exoplanets, and on pulsar astronomy, roughly third, although the association is not exact with people anyway. And we are using a very diverse set of tools, and we are having fun. And without further ado, let's talk about the current state of ground-based astronomy, ground-based gravitational wave astronomy. Okay, so as you know, gravitational waves are waves in space-time.
To change slide, we're still on your title slide.
You are on the title slide.
Yes.
Oh, this is very important to tell me. Thank you. How do I do this? Okay, so now what do you see? Now you see the correct slide?
Yeah, now we see the group.
And we see, yeah, but it's not a full screen mode. Okay, we can manage.
So let's see if now the full screen mode. Okay, so now you see. Okay, so I have a fairly large group and it's roughly divided by 3 parts. And we are using a diverse set of tools. Now you can see the list. Okay, that doesn't matter that much. Okay, so without further ado, let's talk about gravitational waves. So as you know, gravitational waves are waves in space-time.
We didn't see you change slides. If you change slides, we didn't see it.
We're on your
page. Slide. What's going on? Okay, let's use this mode. So here you see when I change slides.
Yes.
Yeah.
Okay, so let's just work with this mode. And I think it's an efficient enough utilization of the screen. Okay. So gravitational waves, they are, as you know, they are waves in space-time. And there had been brilliant and long-standing instrumental work on building a many kilometer scale interferometer that manages to measure the tiny fluctuations in space-time that gravitational waves introduce, that realistic gravitational waves from astronomical sources introduce on the ground. Those are marvelous instruments, and any plot of this instrument doesn't do justice to it. But if you just want to get the gist of it, it's an interferometer. So what you are measuring is the delta length between the two arms of the interferometer. And you are measuring it by measuring the intensity of a laser coming up out of this beam splitter. Okay. And there's long list of things I neglected in this description, but for the sake of this talk, it suffices to understand that you have an interferometer, it has 4 kilometer arms, and that you are measuring the delta length over length. How does the signal look like? So on the left is the first gravitational wave ever detected, this 150914. And on the right was the neutron star merger 17 by 17. Those, I think the one on the left gave the LIGO collaboration the Nobel Prize, and the one on the right gave the LIGO collaboration the Breakthrough Prize, or maybe the other way, or maybe both. What I want you to see from this plot is that, first of all, what is this source? The source is a compact binary, so you have two essentially standard black holes. For the sake of the signal that you're seeing, it suffices to think of them as black holes. And these black holes are in a compact binary, in a relativistic compact binary. So they are in orbit around each other, and their velocities are relativistic. At merger, they get to something of the order of speed of light, so like a factor of unity times speed of light. Unity, let's say half or third or something like this. And the waveform that you see, so here I want you to look on the right, it's kind of this chirp. So what does it mean? It means that the wavelength is increasing with time. And at time of merger, it reaches the typical wavelength of a black hole. So if you take a black hole and you squinch it a little bit, it will ring down, it will have a typical wavelength, and that's the maximum wavelength you will see of the gravitational waves. Maximum frequency, sorry. Good. Yes, so nothing is easy in this field, and this waveform in particular, there was a long-standing, several decade effort from the GR community in order to be able to compute what's going to be the merger of these black holes. And still there are computational problems in the waveform models. Maybe later I'll say some comment about there is even a part of phase space in which this is limiting us, and not the instrument, neither the data analysis. There is a part where it's actually important. Good. What else do I want to say? Okay, so what can we measure? So people usually show these plots, and it's really not easy for me or you or any human to compile how you see these images and you arrive to masses, spins, where is it on the sky. So I'll try to order these things up a little bit. So we have the intrinsic parameters, intrinsic as in it's intrinsic to the system. It's not related to geometrically how you place it. So an example parameter which is intrinsic is the mass of the system, okay, and the spin of and the effective spin of the system. So let's talk little by little. So the chirp itself, so the way the signal is changing its frequency with time, the phasing of the signal, the sinusoid, how it changes its phase, this thing is telling us what is the mass of the system. And it's also telling us some function of the spins of the black holes. So if you have two black holes and they have spins, these spins, they have, those are like three-dimensional vectors in space. And the first order thing to affect the waveform is the linear combination of these spins that is along the axis of the angular momentum axis of the orbit. Okay, so you are projecting this part of the spin, and that's the only thing that you can measure from the phasing to first order. Okay.
That's
what?
This is first order in what? In the magnitude in a post-Newtonian approximation, or?
Okay, so if you want, so we can take it to the next level, if you want. So taking it to the next level, so the phase as a function of frequency, you have f to the minus 5/3. The coefficient of this is determined by the mass. Then there's another correction to this, which is f to the minus 1. And this f to the minus 1 is dependent on the basically the mass ratio and the mass itself. Okay, so it's the mass and the mass ratio that determine this coefficient. And the next coefficient, f to the minus 2/3, is determined by the effective spin and the mass ratio again. But if you have a finite band, and the LIGO detector has a finite band, f to the minus 1 and f to the minus 2/3 could look very similar. And in the end, you have a degeneracy that is high enough that essentially most sources will have some degeneracy between the effective spin and the mass ratio that is substantial to our understanding what am I seeing. Okay.
Thanks.
There's another parameter that you can measure, which is the cutoff frequency. So when the two stars hit each other, you can then think of it as a one black hole that is just disturbed. And this black hole that is disturbed is going to ring down. And the frequency at which it rings will tell you what is the total mass, like the mass that is inside there. And maybe something about the spin, because again, the quality factor of this black hole is determined by the spin. So this bell is a bad bell. It will ring only a few times until it will die. And the Q factor is determined by the total spin and not the effective spin. Okay. In principle, detectable. In practice, sometimes it is outside band, sometimes it is the only thing we see, and then the degeneracy is too big. But logically, if I ask you what numbers can we measure from the waveform itself in one detector, the answer should be the mass, the effective spin, the mass ratio, maybe two numbers out of these three, and sometimes the cutoff frequency. And just the joke is on us, because when the cutoff frequency gets in band to measure, then the degeneracy between parameters is such that suddenly you don't have two phase parameters, you have basically only one, so maybe only mass. So long story short, it's not easy to measure everything at the same time, but I think there's some lucky signal that maybe we have all of them. But that's the exception. Okay. There's also the extrinsic parameters. So what are extrinsic parameters? So these two black holes, I can put them in space in some direction that I can see from the Earth. And maybe I also play with its inclination, and maybe I can rotate the system. So that's the polarization again. And those, what do these things determine? They determine the time delay between the different detectors. So the LIGO detector, these 4-kilometer arms, there are actually 2 copies of it. And there's an additional detector in Europe called Virgo. And the time delays between these 2 detectors are basically determined by the sky position, because of the finite travel time of light between these few detectors. In addition, you are seeing some sinusoid. The phase of this sinusoid actually might not agree between the 2 detectors. So that is determined actually by the polarization. So the detectors themselves, you can rotate them on the ground and you will measure different polarizations of the gravitational wave. And as a result, the phases are not predetermined. And they are also telling you something about sky position and, let's say, polarization angle, inclination and orbital phase. So some combination of those is measurable. From the amplitude of the signal, what you get is basically the mass divided by distance times some sinus of inclination. Okay. So the most sensitive configuration is when the system is face on. Okay. Good. So these are the things we can measure. This is only the first order. These are the things that if you don't have it in your model, you will not detect gravitational waves, period. Okay. Now, if you want to add, there are also smaller effects, but not less important, because sometimes they break the generacies that we really want to break. Okay. So the first effect we will talk about is higher modes. Okay. So the signal, the h of f that you measure, okay, you can write it as a linear combination of several different modes. These modes are, it's a bit counterintuitive. So if you take the binary black hole and you take the instantaneous gravitational waves that this thing is emitting, you can look at it as a function of position of the observer. Okay, so you have a sphere of observers, and you can then decompose it into modes. So there's the you can take the YLMs on this sphere, and then the 2-2 mode, this is the like quadrupole mode, is the main mode of emission of gravitational waves. So so if you take all the observers, what they see, and you make some decomposition, you will get the 2-2 mode as the main mode of emission. But there are other modes. And these other modes are, you can think of them as perturbations to the 2-2 mode, because they are coming with another V over C, with another V over C, yes. And this V over C, so what it means is that when the system is super relativistic, so let's say the black holes hit each other at like half speed of light or something, then you can think of it, there's some beaming of the emission, and this beaming of the emission is actually decomposing to many modes. It's no longer quadrupolar. So one way to think of it is that the more relativistic the system is, the more important is this beaming. So you're emitting in modes that are not the 2-2 mode. So there are other modes. The pattern in the sky slightly changes. So if we look at this number, so there's some GR funky thing. There's the mass ratio that determines how much of this 3-3 mode you will get. And one important thing to say is that the frequency of these modes is not the same frequency. So the orbital frequency is not the gravitational wave frequency that you measure. You're measuring twice the frequency from the 2-2 mode, okay? And the 3-3 mode is actually emitting at 3 times the frequency. So those are the things that are related. So please look at the solid blue and the dashed blue, okay? So solid blue and the dashed blue. So solid blue is the 2-2 mode. The dashed blue is the 3-3 mode, okay? And you could see the amplitude as a function of frequency in this plot, overlaid on the amplitude spectral density of the noise in the LIGO detector. So if the thing is below the green curve, it means it's undetectable. But if it's above, it means that maybe you can detect it. So as you see, that the 3-3 mode is really small compared to the 2-2 mode, okay? But if I take this system and I now push it to the left, so pushing it to the left means to increase the mass, then the 2-2 mode will get out of band before the 3-3 mode will get out of band. And as a result, the highest masses, if I want to discover the highest masses with LIGO, I need to include higher modes in the search. And if I want to break the generacies in inclination and mass ratio, then maybe I also want to include higher modes in my search. Okay, not in my search, in my parameter estimation. So long story short, it's usually negligible, but it can make a difference to the interpretation of very loud signals or to the detection of very heavy signals. Okay.
Doesn't it appear automatically in the computed modes, the ones that are computed numerically?
Nothing appears automatically. You need,
What do you
so
mean? If you do,
so let's put it this way: the first waveform models that people use in
if you
order
do
to
a full
analyze.
numerical simulation, you have these modes.
First of all, in the first simulations, they were not always extracted. So people literally got out the 2-2 mode in order to reduce numerical noise from the simulation. So they were not even extracted in the first go on these simulations. But maybe Ofek knows more about this. But to my understanding, okay, the 3-3 modes, the computation of them is actually after 2015. Okay, so if you look at the papers from 2015, people did not use these modes in the analysis because they didn't know how to compute them even. Okay.
The
So
expectations on the amplitude of the higher modes were available already before then, and because they
the
were
expectations, yes, the PN. So what I show here, this is the PN. This is the PN description of the higher modes. That is available, but if you want it in near merger, then you need the simulation. There's no. I mean, we actually quantified in order to build the bank. We quantified how good it is. It's usually good enough even for parameter estimation, but that it's not the full story anyway. Did I answer your questions? No answer. Okay. And so there's another secondary effect, which is called precession. Okay. So what is this? So first of all, I wanted to look at the signal. So instead of being a beautiful standard chirp in which the strain is kind of constant or maybe a little bit decreasing or increasing with time, but maybe decreasing with frequency. Instead of this, you have this wobbly thing that goes up and down in amplitude. And this is what this means is that the system, instead of standing in place in the same plane and doing its rounds, the plane of the orbit is actually changing. So you're seeing the same system, but from a changing observation. That's another way to look at it, that the observer is kind of moving with the thing. This thing can happen if the spins of the black holes are comparable in magnitude to the spin of if the angular momentum of the black holes is comparable in amplitude to the angular momentum of the orbit. Okay. Now, in that case, you will see this precession, and this precession can be very wild, as this signal shows. So in this signal, it's not a perturbation; it's a leading order effect. But this condition that the angular momentum of the orbit will be comparable to the angular momentum of the spins of the black holes. This requires some special conditions to happen. So first of all, it needs to be very relativistic. So the system, like near the end, it's more important because the angular momentum of the orbit shrinks when the system becomes more and more compact. Okay. And the other thing is that you require that the mass ratio will be large. So why does it help? So if I put a big spin on the big black hole, and then I shrink the other one, when I shrink the other one, I'm shrinking the angular momentum of the orbit, but the angular momentum of the big black hole is fixed. So I can get the spin of the big black hole to even win and beat the angular momentum of the orbit. And as a result, when it comes from far away and it gets closer and closer in, at some point they will be comparable and the system will go very wild. Okay.
So this waveform that we're seeing here is an extreme mass ratio in spiral into a rapidly rotating black hole?
So I wouldn't use the keyword extreme mass ratio. because it's kind of used for some orders of magnitude that I don't have, but this at mass ratio of more than 1 to 2, you will begin to see precession. At mass ratio 1 to 4, it will be easily visible, and at 1 to 10, you cannot work without it. Okay, so
okay. And
so
this is a numerical, it's a full numerical simulation, or it's some other?
The thing I'm plotting here is not a numerical simulation. I'm plotting here some waveform model. And what I want to say about this is that the numerical simulations are dense enough in phase space until mass ratio roughly 1 to 4. And there we really have a waveform model that is accurate enough to use in parameter estimation. Beyond mass ratio of 4, there begins to be calibration issues with the waveform model. They will still spit out an answer, but now there's no guarantee that it's correct. And whenever people try to calibrate it, we see that there's work to do. Okay, so long story short, let mass ratio more than 1 to 4, and there's, especially for precessing systems, there's really lots of numerical work to do in order to support observations that are already piling up. Okay, so we already have signals in which we are analyzing with waveform models that are not calibrated for the mass ratio that we are seeing. Okay, so it's already happening. And you're saying, what do I care about this calibration? But at some point, it will also begin to interfere with the interpretation. Good. So I think I said every point in this slide, except for the fact that the most important part of precession is NSBH, so neutron star black hole. So by definition, neutron star black hole will have a big mass ratio. And in that kind of system, maybe we are missing the bulk of it because we are not searching for precession. So I didn't say this, but currently none of the searches is really searching for precession. And when you look at the NSBHs that we did find, they have spin 0, and I think it's not an accident. Okay, so this is my personal view here. It's not objective or accepted in the community.
Is this black hole spin or NS spin?
What?
Is this spin 0 for the black hole or for the neutron star or for both?
So for the neutron star, it's not affecting the measurement much. Spinning the neutron star in an NSBH merger doesn't change anything. Because the neutron star has a small mass and it supports doesn't even support very high spin. Thank you for the question. There's another secondary effect, which is the formability. So if you have a binary neutron star, and especially if you have one of the neutron stars being relatively light, okay, and because this deformability is a very strong function of the radius, I think it's radius to the power 5, it actually matters is it a 1.7 solar mass neutron star or a 1.2 solar mass neutron star. The change in the deformability will be very large because it's a really different size of star. And there's an extra phase at large frequencies that this thing is incurring. So what's happening here? So what's happening is that the neutron star deforms when like during this orbit, and it changes the what does it change? I think it changes like the equation of how you translate energy into the energy of the binary as a function of separation changes when you can deform the neutron star. We have an upper limit for this effect from 1708-17. But it's only an upper limit, and I want to say about this effect that this effect could get measured tomorrow, because if we would have detected 1708-17 like signal, so like the same SNR, but the masses were lower, we would have detected the deformability. Okay, so it's just about like, would we be lucky and see neutron star mergers that are low enough mass?
Well,
so
all
this could
it would have to be closer for the same SNR.
So the SNR is kind of a secondary effect here. So the SNR does improve your detectability of the deformability, but let's put it this way: if you put me in charge of what to do, I'll put it twice further away and make the mass very small, and you will make the measurement will be a cheap piece of cake. And if you have something which is heavier at the same, like even closer than 17 by 17, then it will not deform. The deformability will happen at some frequency, 3000 hertz or something, and you will not measure it. Okay, there's an additional effect that is not so much talked about in the community, I think. So there are special frequencies to neutron stars. For example, if you have a neutron star and it rotates, then there are some special frequencies that this thing can support. I don't remember if it's G modes. I think it's G modes. I'm not sure about which particular mode it is, but I think it's G mode. And once the orbit is exactly this frequency and you squish the neutron star at this particular frequency, then you can dump energy into this mode. And then you have, if you look at the frequency evolution, at the signal with the frequency evolution, then you will see a phase jump at particular frequencies. And those would correspond to some combination of the mass and the spin of the neutron star. This effect is very subtle. Some of these frequencies are supposed to be universal in terms of, like, if you know the mass, you know the frequency. Some of them depend on the rotation of the neutron star. Okay, so these effects exist, and maybe they are detectable. I'm not sure. But all of these effects are very strong functions of the neutron star masses, and if we get lucky, and LIGO has a significant amount of luck that it gets. So if we get lucky, then we'll measure these effects just from signals that have low mass. Okay, so questions concerning binary black holes. So we before the discovery of 1509-14 by the LIGO collaboration, we did not know of black holes of these masses at all. Okay, so it was a complete surprise. I wouldn't say that it blew everyone off the water, but it blew 90% of the people off the water. Let's put it this way. Some Russian people said it before, but okay, that's standard. The key question currently is, how do they form? And we really, like, long story short, we don't yet know, although we have a way to kind of map what could be. Okay, so a key question is, so I have two black holes. Did they form together, or did they assemble after they were black holes? Okay, so forming together means that they formed through binary stellar evolution. There's a key prediction that the spin of the black holes, the vector in 3D in which a black hole chooses to spin on, knows something about the orbit when it formed. So for example, the star right before it became a black hole could have been locked tidally to its friend. Okay, it can happen. So this could generate an anisotropic spin distribution, and could even show a possible prevalence of maximal spin, although the physics of how does a spin of the star goes into a spin of a black hole is very unclear. And even if you have more than spin one angular momentum, it's not clear that you can get all of it into a star. So for example, if you have a bathtub full of water and you have a bucket and you want to fill the bucket with the water, if you put all the bathtub on the bucket, it's not clear that the bucket will be full in the end. Okay, so there will be many things happening. Dynamic formation is a slightly more interesting situation in which you have a conglomerate of stars, either near the central black hole of a galaxy or just a globular cluster. And this conglomerate of stars the stars become black holes on their own, and they decide on their spin from single stellar evolution. Okay, and then these black holes, they interact with the rest of the stars in the cluster through some statistical physics interaction of these black holes with the other stars of the cluster. They might actually sink to the center. And after they sink to the center, they could find each other through free body interactions and form very compact binaries. And these compact binaries might actually merge in the cluster, outside the cluster, but this thing can actually happen. The key prediction of this scenario is that the spin of the black holes knows nothing about the orbit that they will find themselves in the end. And there's another key prediction that these triple body interactions, they might actually lead to formation of a system that is so eccentric that after one of those very close approaches, it will just merge. And what you will see is an eccentric merger in band. And there's an expectation of a few percent. Now you can discuss with people in the community whether it's 0.5% or 2%, but there's a clear prediction that it should exist eccentric mergers. And there were in the past some questions with respect to the maximum and minimum mass of a black hole, of a stellar mass black hole. So if you ask 5 years ago in the community, what's the maximum mass of a stellar mass black hole, people would recite either 45 or 55 solar masses because of the mechanism of pair instability supernova. And there was a key prediction that no component of these binary black hole systems could be more than 55 solar masses. And if it's already more than 55, it should go all the way to 200, because maybe over there it's allowed. And there was another a bit weaker prediction that core collapse supernova will make no black holes below 5 solar masses. I don't know what's the theoretical standing of this statement was 5 years ago. I don't know what it is now, okay, but let's wait for it. So what are we finding? So this is taken from the GWTC catalog published by the LVK. This is the mass distribution that they have measured for the binary black holes. As you see, this distribution has some features. So let's talk about like the general trend. The general trend is that there are less black holes with mass. That's not a big surprise, okay? The detected distribution is you have more detected events in higher masses, but that's just because we are seeing them further away. In terms of features in this distribution, so I think it's fair to say that the maximum that you see at 8 solar masses is probably real. I don't think you can make the distribution such that there's no peak over there. The other peaks, we can talk about this, okay? So the middle peak, I think it's not necessary by the data. It could be just a fluctuation. And the final peak before some drop in higher masses, that I'm also not sure, because maybe it's some prior, it could be some prior issue in the parameter estimation details. There is a small question mark about is there a peak there or not. The fact that there is a significant drop at higher masses, that's also not a big discussion. There is a significant drop, but it's we can talk how strong is this drop, but you cannot just continue with the regular rate. In terms of mass ratio, there are some 12 events with Q not equal to 1, and some 80 that are the Q is consistent with 1. Consistent with 1, so it just means that we could not refute that the mass ratio is 1. Faint signals, as I said before, there's degeneracies between the spin and the mass ratio, and not always you will know. Okay. Studying the symmetry of the effective spin, here we can say a bit more. So just if you go over the catalog, you count how many positive spin, how many negative spin. And by positive, I mean definitely positive, like you reject negative completely. And negative, I mean you reject positive completely. The distribution is like 10-0, okay? And I mean, we tried to make some quantitative statement. So for example, make a plot of the CDF of the spin versus how many numbers, and maybe normalize it by the measurement of zero spin plus some excess. And really this asymmetry of positive versus negative is caused not by very high spin events that maybe we don't see their negative spin counterparts because of selection effects. It's actually caused because of high SNR events that have a very low spin, but detected and positive, okay? And we don't have the counterpart that is detected and negative and small, okay? That does not exist, and there is no much selection effect between spin of 0.1 and spin of minus 0.1, almost nothing. Okay, so what do we know about the key questions? So we have a big X on the maximum mass of the stellar mass black hole, because so back in 2002 we found an event that had a too large a mass, and people told us that it's a glitch because it's too large a mass. And then in 2003 the collaboration had found 3 more friends to this signal. So now it's very clear that that one was correct and the other ones are also. There was a big surprise in 2003 when they found events below 5 solar masses and even below 3 solar masses, which is even confusing. Is it a black hole, a neutron star? What is it? What's going on? In terms of the formation mechanism, I put a yellow cross on the dynamic formation, because for me, first of all, it's not a consensus in the community. Okay, so now it's an opinion. For me, the 10-0 is super convincing, and it's very clear that dynamic formation could not be the full reason. Now, we do see evidence, okay, that there is a distribution of things that have spin 0, okay? And those things could form in dynamic formation. I mean, maybe 20% of the signals are from dynamic formation. I wouldn't know, okay? But the bulk distribution, the most of the signals, is probably not dynamic formation. So I would put a yellow X over there. And we do see anisotropic spin distribution among the signals we detect. The questions about binary neutron star and NSPH are even larger. So first of all, what's the rate of this thing? So we saw 2 events of 2 of each, and that's not enough to determine a rate in a reasonable manner. There was association with a GRB for 170817, but we don't really know, would it happen every time? What is the duration of this expected GRB? I mean, there was a long-standing expectation from both Tzvi Piran and his friends, and maybe even other groups, that there would be an association between a GRB, a short GRB, and a gravitational wave merger. But now that we have detected one, and for me it's a big riddle, the duration of the 2 seconds and also the delay between the signal and the merger of the 2 seconds. So I would say that the association with the GRB, there's many questions regarding it, and we really want to resolve them. And currently it seems that we will have to wait until this becomes an industry, that you will have 10 of those per year. The kilonova and the formation of heavy elements, there are questions. So I think there's no discussion. The question about the heavy elements, I think, is done, and we know that kilonovae have heavy elements, the 1 kilonovae that we saw. But now when you try to translate this to rate and to abundance of elements in the universe, then again begins the questions with orders of magnitude uncertainty. So we still want to resolve this. The equation of state of the neutron star is still unknown, and LIGO actually has a fair chance of measuring some of it. So as I said, you could measure tidal deformability from maybe a lucky low mass neutron star merger. We could measure the maximum mass of the neutron star, but I'm not sure how LIGO would know it's a definite neutron star. So maybe you'll have to also have a GRB at the time. And
So
there's also
on that point you list 2 BNS events and 2 NSPH events. That's solely from the masses, right? We don't actually know,
yes,
other than the
that's solely from the well, for 170817, you know there was a neutron star involved.
yeah, that's the only one.
Okay. And instabilities and special modes might actually also tell you something about the equation of state of the neutron star. Good. So what are our efforts? So in the last 10 minutes of this talk, what are our efforts to study the origin of the compact objects in relativistic binaries? So first of all, why are we talking about this? Maybe why don't LIGO do it themselves? So we've shown in the past that it's valuable to have an independent pipeline because we have shown improvements to the analysis that, by the way, since then found themselves into the analysis of the main LIGO analysis. Okay, but we found improvements to the volume. So this is a table from our O2 analysis versus the LIGO O2 analysis, and there was a full factor of 2 in the volume of black holes that we could see, and it was really like a combination of many different effects. And the totality was that we doubled the number of events, both like you could measure from the pipeline that we should have doubled it, and we doubled it in practice. Just one thing to say about why does it make sense to have my group all over astronomy is that the techniques that we've used in order to detect gravitational waves, we are now actually using them. So Orina, my student, is actually using them in order to measure eta Earth from the Kepler data, completely different scientific case, but the same methods and the same. If you read this pipeline, it looks like our detection pipeline.
What's eta?
Okay, what?
What is eta?
You can ask Corina later. So it's in the final. Parts of the analysis.
You mean that you don't know what eta is? What is the meaning of eta?
Oh, the meaning of eta I do know. The meaning of eta is the rate of solar mass, Earth-like planets around solar-like stars. Okay, so that's something that you want to tell your grandkids maybe. Okay, so what are we doing about the questions? So first of all, if we want to study the highest masses, we should include higher modes in the analysis. And we've just published a paper in, I think it was already 2024, I'm not sure, led by Jay, which is a postdoc at the IIS. And we included higher modes in the analysis, and we have detected events at the highest masses that the band of the detector supports. We also, so this is a new plot, it's not in the paper. We also show that precession is not important at these masses. So it's really just higher modes, and we have now an okay to go and do a population analysis and see whether we can extend the mass function of the binary black holes based on these new detections from Jay's work. Orina, when she's not doing planets, she's trying to add precession to the search. This is an even more involved task than adding higher modes, because the complete setup of the search breaks when you try to add precession. So the first thing that breaks is that you cannot use a random placement bank and just do whatever. You have to really work in order for the number of templates not to explode to billions. Okay. And we are using some genius decomposition of Stephen Fairhurst from 2020, in which he managed to decompose precessing waveforms into non-precessing waveforms and actually explain why exactly would it happen and how to extract these harmonics. And we can use this in order to build a bank that is feasible to run and very efficient in the search. So Orina is doing this. Adding precession, okay, so I already said this slide. The next thing you need to do in order to add precession is, suppose you find the precessing system, you need to be able to do a PE for this. You need to be able to do PE for this regardless. And when we began this project, PE for precessing system could have been weeks of computation. And Javier and also Jonathan were working very closely on trying to get the parameter estimation of these precessing systems into something that goes from weeks to minutes. Okay, so Javier has a code called Cogwheel. Javier is a part of our collaboration, and he has a code called Cogwheel that is using a few fantastic tricks like quasi-Monte Carlo integration of the extrinsic parameters and some natural coordinate system that will actually make sense to represent the spins in. And it really works, and it's fantastic. But that actually is not good enough, because if you want to add precession to the search, there's another detail, which is the signal at each detector is now going to look different in terms of the precession. And if you really want to coherently analyze the signal, you have to compute this evidence integral. So Jonathan, my student, is working for the last year and a half, I think, something like this, on getting this evidence integral not into minutes but into seconds, and also without any intervention of a human. It's like an integral in the computer. And we found some factorization in which, instead of, so a regular sampling scheme uses some 10 to the 7 samples, each of them, it is evaluating the likelihood. So it's evaluating a waveform and then the likelihood. And the reason why it takes so long is because evaluating a waveform and the likelihood is something like 10 to the minus 2 seconds if you have like a super optimized code. And the magic integral, the premise of it is that you separate completely the degrees of freedom of intrinsic and extrinsic parameters. And you manage to make the full coherent likelihood a dot product between some tensor including intrinsic parameters and some other tensor including extrinsic parameters. And as a result, you can compute a likelihood in 10 to the minus 9 seconds. And as a result, even if you have a much worse sampling scheme, so the sampling scheme of an adaptive code is much better than something stupid that we would do ourselves. But since you are computing the likelihood 10 to the 7 times faster, maybe you will actually maybe it is actually beneficial. And Jonathan, I'm still demanding this 10 seconds. So don't settle on 100. Now, can we also improve the multi-messenger part of gravitational wave astronomy? And it seems the answer is yes. So my student Ariel is working on improving the analysis of GBM. So GBM is the main satellite that detects GRBs. It's the main all-sky satellite, I should say, that detects GRBs. And it turns out that the pipeline is not state-of-the-art. And you can, if you work on this pipeline with the same rigor that we worked on the pipeline for detecting gravitational waves, with the same methods, by the way, it's literally a translation and maybe a little bit of adaptation to Poisson noise. We can improve the GBM search by a factor of 4 in sensitivity. That's not the 30% in LIGO. Okay, that was a big deal. Here it's a full factor of 4, and it will take you a factor of 2 further away. And this also is expected to increase the amount of multi-messenger events, GW versus GRB, because as you can see, so here in the plot, you have the viewing angle from the jet. The GRBs, they go outside the screen for the very small thetas, so you can see them very, very much far away. Okay. In the y-axis, we put the actual volume of the universe that is captured by this piece of phase space. So it has a sine theta and a d cubed. Okay. So we are seeing GRBs to the edge of the universe when we are observing them from a few degrees. But when you observe them from 20 degrees, your signal is very, very, very weak, like the 170817 signal that was observed from 23 degrees away and was 10 to the minus 4 fainter than a regular GRB. So if you improve the GRB search, you will have a little bit extra angle. And if you improve the GW search, you'll have a little bit extra distance. And the product of those areas is the important product. And therefore, improving the GRB search is just as important as improving the GW search if what you care is multi-messenger events. And my two last slides is that there's an effort in Weizmann, as you know, there's Ultrasat, the satellite, that will be the best game in town for searching the kilonovae in 2027 when it's launched. And there is some interesting question of how to analyze the data from it, and we had to solve it. So my student Matan had to solve it and did a marvelous work, and now he's at the high tech, so we're all sad. And last, the data of LIGO is not given from God. The data from the detector is actually accompanied by many auxiliary channels that are controlling many degrees of freedom, and in particular in low frequencies, so frequencies over here. So this is a plot from a LIGO paper. I apologize that there's no reference. The fundamental noise sources, which is this purple curve, okay, purple plus red is fundamental. The fundamental noise sources are not determining the noise that you are seeing here. The noise that you are seeing here is some noise from the control system. And this control system is monitored and recorded. And it could very well maybe that an analysis that is beyond linear subtraction, which the LIGO collaboration already does, an analysis that is beyond linear subtraction could actually improve the sensitivity at low frequency. And if you could really improve the sensitivity at low frequency, you would resolve many of the degeneracies, the chi-Q, the precession, everything. And a student of mine, Sancho, will work on this. We recently applied for LIGO to get the auxiliary channels, and a week and a half ago, they answered yes, and they gave us the channels. So now we have no excuses, and we work on this. And that's it. Thank you.
Thank you, Barak, for a very interesting talk. Any questions?
Yes, I have a question.
You're muted, Barak.
I thought,
You're
okay,
again
I
muted.
pressed the button. Can you hear me now?
Yes.
Okay. Okay, so thank you for an interesting work and talk. I have a few questions. The first one is about the non-chirp waveform that you showed. You showed it last on your slide number 20. You called it a wild precession or something. Yes, so it's the upper one. You also showed it separately in an earlier slide. My understanding is that this was not observed, but this was seen in computer simulations. Is that right?
I wouldn't say it is not observed. I would say that we are not searching for it. We might see residuals of it in some things that we have observed. And I think there's a particular signal in which there's discussion, is it precessing or is it a glitch or whatever?
Look, Barak, if we were not searching for it, then for sure we haven't observed it.
Yes, but I'm telling you, we are not searching for it, but there is this regime in which this effect will be subtle, and then you would detect it even though you would not search for it. And then when you try to do parameter estimation later, you would infer, there was some extra 10 points in chi-squared I could have gotten, and you would know this from the parameter estimation. even though you did not search for this. So this is possible, and it in fact happened.
So thank you, and I would like to comment that this relates to one of the early famous plots in the business of gravity waves. There's a plot by, I believe, Kip Thorne that said, we know how the waveform should look initially from Pn. We know how we should look at the end from ring down, but how does it connect? It could be just the smoothest connection, which is the chirp, or it could be something more wild. And the conclusion used to be that the previously observed and previously simulated waveforms were all the minimal chirp. And I think what you're telling us that the wild possibility is also possible, although obviously it would be more rare.
Well, I wouldn't say obviously more rare because we are not searching for it. So finding it is it's a bit tricky to tell something about the rate.
So maybe even it's very common.
It could be. So for example, the fact that the NSBHs that we found has both spin zero, I think it's very telling that we might have missed things that are not spin zero just because they are precessing. But you know, it's all until we do this search from start to end, we will not know. So this is why we are intensively working on this. So two students in my group, and also Matthias is heavily involved, and Teja. So it's a large effort in our group, and this is because we are very curious about, do these signals really exist, and what does it say about NSBH spins, yes or no?
Thank you. A second question, unless somebody has an urgent question, is about the post-Newtonian order. I was involved in work to compute post-Newtonian corrections to simulate the signal when it is far away still from merger. You can get analytical results for the behavior of the system and the form of the waveform. And people now go to very high PN orders. They go to 4 or 5, and they say that Lisa will be sensitive to it, or maybe LIGO is almost sensitive to it. I'm curious to hear your perspective. How many PN orders, if you have such a perspective, how many PN orders are actually effective right now? Because as you mentioned, there is very wide errors on the spins and the masses. Well, not so the masses, but more so the spins. And are the higher PN orders effective at this time?
Okay, so first of all, there are sometimes very high PN orders that are not such a small perturbation. So for example, the deformability is, I think, 5th PN order, right? But it is still important because the constant that it comes with is actually a big constant and not a small constant. And so it can happen that you need a high PN order just because of prosaic reasons. In terms of the need for it, so if we really manage to expand to the left, so instead of having the signal detected from 30 Hertz, if we'll have it from 10 Hertz, there will be substantially less degeneracy between the first modes, and then maybe you will need another PN mode. And last, I would say that I think these high PN orders are very important specifically for precessing systems, because it seems to me that the high mass ratio regime is kind of inaccessible to the numerical simulations. And there it seems to me that PN orders are the way to go in order to analyze precessing systems. So it's really important, in my view, in order to get NSBH to be accessible both theoretically and in practice.
Okay, I have some comments about what you said, but thank you. And the last thing that I want to ask you about is about non-circular mergers. So we know that
eccentric mergers, you mean?
Yes, exactly. We know that all binaries circularize, and this is the usual assumption. But if a binary is created in a very eccentric state, it could also merge in a very eccentric state. And my
Yes.
question is this something that people are actively looking at right now for these possibly
So we are
rare?
trying
I
to
don't know.
develop such a pipeline.
You mentioned this already?
We are. I didn't say this because this is very recent, but like as of the call yesterday, we are trying to develop an eccentric merger. So my collaborator Tejas Nadav has a student that this might be his project.
I see.
And we also try to do this, and I think there's also efforts from other parts of the community to do to add eccentricity into the bank. And I think there was even one search by the AEI group. So precession was not searched, I think, but eccentricity, I think there are already implemented searches. Maybe I think well, Alex Nitz is no longer at AEI, so I don't know how to call this. So maybe the Syracuse group. Okay,
so this is a group within LIGO or outside?
No. Within LIGO, it's very opaque to me. I don't think there's an official LIGO search for eccentricity.
There's an official.
Maybe Ofe can comment about this.
There's an official LIGO task force for eccentricity, and we're trying to promote it now for O4A and O4B. We're definitely concerned with eccentricity.
Eccentricity task force. That sounds great.
Sounds very military.
Yes. שלום לבת החמודה של ברק, אני מצטער שאנחנו גונבים את אבא קצת הרבה.
Okay.
Okay, thank you very much from my side. You answered all my questions. Thank you.
Any more questions? Okay, so we had quite a lot of questions. So if there are no more urgent ones, we'll let Barak get back to his family. And thanks, Barak, for a great talk. And
thank you.
Goodbye, everybody.
Bye-bye.
ברק, אני רק אגיד על השאלה על קיפסטוין. מה שברק הראה...
ניסיתי להגיד משהו, רק